just like that. All right, cool. Awesome. All right, so I just want to say thank you guys. This really means a lot to see all the interest in this topic. This is something that's really near and dear to my heart. It's really been kind of like a, has just been a never-ending journey, right? I'm still learning about machining, but it's really kind of gotten me on this path, and it's such an immense topic. So I'm going to try to do the best I can to kind of cover. Really, I'm going to start with the basics, and then hopefully by the end we can get into some pretty unique stuff. So if you guys have any questions as we go through, just feel free to stop me on the slide that we're on. I'm going to have some time at the end for more questions if you think of stuff like later on, but just raise your hand, let me know. We can talk a little bit more about it. But again, it's a lot of detail, so I'm going to try not to like bore everybody, but I do want to cover. I know there's a lot of interest and there's a lot of really important things to consider in this kind of world of machining. So for me, like this is just kind of what I was able to put together. So again, welcome. A little bit about myself. So if you don't know me, I've been here for a little over 2 years now. My name is Kevin Heidorn, and I went to Cal Poly Pomona for mechanical engineering. Just over the hill here. Go Broncos. So currently I'm working here as a mechanical engineer for Wavestream, and again, a little over 2 years. But before I did this, I worked in the aerospace industry for a little over 9 years. And so what we did there was a lot of, aerospace structural components, big assemblies, smaller detail parts, surface prep, a lot of anodizing, that kind of stuff. And overall, we had, pretty big primary customers. We were delivering directly to, Boeing, Raytheon, and Airbus, and some pretty big names on there. So we were kind of that last line of, what you call almost a prime manufacturer. And so we had sub people that we would work with as well, but we were kind of that last line of defense that when we deliver that part, it's going off to get usually bolted right up to either an airplane or whatever the application is. So kind of similar to what we do here at Wavestream, right? Throughout just my career so far, just so you guys have a little background on me, I've got some certifications in like CAD tooling design, simulation analysis using like finite element analysis and stress and thermal, and actually done some thermal and vibration classes here at Wavestream, which have been really helpful. And I've actually taken classes in doing full-blown composite repairs on like wings, for example. If you have like a bird strike on a Cessna, you need to repair that. I actually have a background in stuff like that. Been associated with some green belt manufacturing projects, which are really helpful in kind of understanding how to be efficient with production. And just generally, composites manufacturing in general just really opens a lot of doors, right? So I was always interested in trying to, understand what all those variables are and how to control them, right? Because everything kind of adds up, and that's the biggest thing that you learn when you're trying to do any type of production. It can be something small, but at the end, it can really have a big impact. So again, just me being a nerd, I just really wanted to try to understand every little piece and how they all work together. And that's really what kind of led me down this road. So the agenda today. So first off, I just want to cover just some basic kind of history and overview of how machining and things like this came to be, right? Like how did we get to this world that we live in that is possible because of machining, right? So we'll go into some of that. We're going to talk about the different types of materials. I think having a basis for material science is really, really important in machining. It's you are going to be kind of, it's really the alphabet. You kind of need to know what materials will do, what they're made of, and how they interact with each other if you're going to have any hope of carving it into a nice, beautiful shape at the end, right? So we're going to talk a little bit about that. We have some work holding types. So we'll talk about just really being creative problem solvers. When it comes to this, you have to use your brain a lot. You have to, there's not like you can't Google some of these things and say, hey, what's the answer to this? Because no one's ever done it before. And so you're constantly trying to figure out, new ways and better ways to do it. So we'll look at some options there. We'll just talk a little bit about fundamental kind of shop equipment and what it takes to really, before you can even start machining, there's a lot of decisions and early steps on before you can get to the fun stuff. So we'll talk a little bit about the tools used to get us there. And then we're going to talk about, we're going to get into a little bit of depth on cutting tools. So we'll go through that. Speeds and feeds is a really important topic. I know there was some interest in that, so I want to kind of go over just those are general guidelines on how to run machining, and then we're going to talk hopefully about manual versus kind of automated machining, because they're two different branches entirely. And then hopefully if we have some time at the end, I also want to get into some basic like CNC programming for you guys, so you have a little bit of an understanding of how it works. And hopefully we can even do like maybe an example problem. So that's in there. And again, there's quite a lot of topics here. So kind of finish it up. If we have time, I'll go through what our internal capabilities are here with our shop here, and so what you can expect to just do if we need to do a job in-house. And then we'll go back and have time for questions at the end, hopefully. So let's get started. Definitely got a lot to cover today. So feel free to stop me along the way again, but I'm just gonna get going. So history of machining, right? Now, if you think about this, I mean, we go all the way back to when we were, back in the caves, right? I mean, the cavemen were making rocks and arrows and things like that out of what they had laying around. So that ultimately really is machining. If you go back far enough, we're trying to use a tool to form something into a useful shape, right? So, and there's actually been evidence of even other species, not even humans, that use tools, right? So this has been around for a long time. And I didn't really want to go into everything between 10,000 BC and the last 60 years. So I'm just going to kind of like jump ahead a little bit. There were some really important things that happened kind of really about like 1870 was when a lot of this stuff started happening. We'll talk about that later. But if you look through this slide here, what you'll see right here is this is actually a turret lathe. So these are actually some really old early machines, and a lot of this came about if you look at this time frame. We're in World War II right there. So war is always driven like big production on a big scale, and it's driven a lot of innovation. It's a sad and unfortunate thing that we have to kind of deal with, but at the end, these are some positive outcomes from it. And if you kind of zoom ahead here to like the 1970s, this machine here, it reminded me a lot of one that we actually had at our last company. And it was called Big Blue, and we still used it in some production processes. And it actually ran on something called ticker tape, which you'll see right here, which basically just has a bunch of holes in it. And that is actually one of the earliest CNC programs that's like ever been, really, like when we were first starting this out, what you would do is you would actually feed this tape through, and it would read the codes, and it would fire motors to move in a certain feed rate and actuators to kind of move around. And so you could write really basic programs, but it's a very simple, very elegant code, I guess you could say. But fortunately, we don't have to use that very often anymore. And we got into in the 90s, we started seeing a lot more of these vertical mills. You'll see Fidal, you'll see Haas. There's quite a few manufacturers. Haas is actually up here in Oxnard, California, and they do all their production there. And then, I'm actually pretty familiar. This is a FANUC control, so I spent a lot of time staring at this thing and learning how this works. And then, on a larger scale, we have, these machines can be absolutely massive. I mean, you're talking, they can be bigger than this whole room, all the way to the wall with the offices in the back. And they'll have, a big gantry that will move. And the amount of mass and precision that's moving on this stuff is just, it's unbelievable. So hopefully we'll kind of get into some of that. So just to get started here, really, there's three things. I was trying to break this down. What are the three kind of most important things, really, when you're thinking about machining? And for me, it really breaks down to you have hardness, you have heat management, and you have rigidity. These are like the three kind of biggest variables. Everything else matters, but if you're not able to kind of work with these, you're not going to have anything that works in your process at the end. So just generally, kind of going over hardness, I think I'm going to spend a little bit of time talking about hardness because it's such an important aspect. But everybody's familiar with hardness. They all hear this word, but and I think you kind of have like an intuitive sense for it as a kid. Even just like, oh, my nail can scratch this, or that scratched me, that hurt, right? So you get this idea pretty early on about hardness. And we actually have some pretty interesting ways to kind of measure hardness. So this is called the Shore scale. And this is really used for like very soft things. The hardest thing on here is a hard hat. And today what we're talking about, a hard hat is not very hard. So we're going to kind of go past that. But I wanted to show you that there are some actually really scientific ways to measure hardness. And a lot of it just really has to do with the amount of surface deformation that can be happening on parts. This is what you call a Mohs hardness scale. So this is actually a really general, basic understanding of hardness. Again, when you're a kid, you start to learn, hey, my fingernail can't scratch the copper coin, but the knife is going to cut me. Kind of, you start to figure this order of magnitudes out. And as we go up the scale here, basically the harder the number it is, all the way up to 10 being a diamond. The diamond is basically that's it. Like that's one of the hardest things that we really know of. And then down from there, you'll see some stuff here on the left side. This is going to relate. So I put these in here because they were kind of missing. These are just general minerals that come out of the earth and where they race. Like talc is used like chalk, right? Like talcum powder. So that's obviously very soft. You can spread it out. And we have a huge range in between. I'm sorry.
Yeah. What are units of this number?
Yeah, so it's actually unitless. It's dimensionless. If you look at it, there are no units because it's just a 1 to 10 kind of relative scale, right? So that's a great question. But yeah, these are unitless. So what you're going to see here is carbide is really important. We're going to talk a lot about carbide today. We're going to talk about HSS. This stands for high-speed steel, and then aluminum, right? So you can see aluminum's way down here, like 2.5 or 3. We've got high-speed steel right in the middle there, and then carbide's nearly as hard as diamond. So just kind of keep those figures in your head when we're talking about this stuff. And so again, I'm not going to go into all this words, but I did put a lot of information into this PowerPoint. So if you have more curiosity or you have questions later, just go ahead and refer to the slides, on your own time. But the ones I did definitely want to talk about were, composites. We have, composites are generally things that are made up of more than one material, right? And so like a composite, you'll see up on there CFRP, that stands for carbon fiber reinforced polymer. So you guys have probably seen like carbon fibers before, but these are basically textile materials, and they're almost like rope with some carbon on them, and they're actually pulled under tension while they're burnt. And then what we do is we actually reinforce those fibers and those weaves with a polymer resin, and we cure that into a nice hard state. And so that will have a certain amount of hardness. And these are actually really tricky to machine because they're very, very abrasive, right? And so this is something, I'm going to go ahead and pass these parts around as we go through. Just to note, some of the edges are a little bit sharp, so just be careful when you're passing it and you're handling it. But feel free, if you guys want to check some of this stuff out, I'm going to, as we go through the presentation, I'll be kind of passing. Then we get into metals and alloys. This is easily the biggest chunk of the whole thing, right? So metals are generally really common in machining just because they have good strength properties, right? I mean, you'll see there's metal everywhere in this world. So we want to be able to kind of mold and form and shape this stuff into a certain usable form, right? And engineer from that. Then we have ceramics. Ceramics are a whole different class of materials. They're usually, there's some pre-processing that's done before you kind of finish. So you can think of ceramics generally as almost like kind of a paste material. So think like, say, for example, you take some chalk and you kind of smash it up and you mix it with some water and you make like a kind of a soft like toothpaste sort of deal, right? Well, what you're going to end up doing with ceramics is you end up actually having to later cure these parts, and then you do some final machining after that to get to your final dimensions. So if there's questions on that later too, I'm going to go into that. But just I think those are made up of like smaller particles that are cemented together. And carbide itself is actually made that exact same way. So what we do is we take like tungsten and we take some cobalt and we take, the binder is actually cobalt in that. And there's some other smaller alloying elements, but generally you're going to basically have this kind of nice pasty thing and you're going to stick it in a nice oven and fire it. And then when it comes out, it's very, very hard, right? But we'll get into something later called brittleness, right? So that's something to keep in mind with ceramics. And then semiconductors, I'm not going to go into that because hopefully we all kind of have a good idea of that. But we, sometimes you want to machine semiconductors. We want to machine these PCBs, right? And so those are actually pretty similar in a lot of ways to this carbon fiber part. We're just using, fiberglass and it's still going through the resin. So again, very, very abrasive materials. So moving forward here, these are some really, really exotic materials. So kind of bring it all together, right? Secret recipes. We've got mom's chili up there, right? How does she make that? Like, what makes it really, really special? There's something to it. There's going to be some special ingredient that, keeps you coming back. I can't quite do it without that little thing, right? So these secret recipes, are actually really important in creating what's called these exotic materials. So you'll see here, you'll hear these words like Inconel, Hastelloy, Waspaloy, as we go down here, Nitronic, really popular one. And then, of course, titanium 6Al4V, which we actually have some pieces of here today as well. So this is a piece of titanium 6Al4V. And so I'll go ahead and pass this around. Next, it's a machine part. And the machining that goes into something like that is definitely a bit different than what you would do with like just a standard aluminum. So really the reasoning is these materials do not like to hold any kind of heat. They're very heat resistant. So we use these in like high temperature applications. For example, inside of a jet turbine. So these blades here are actually these really exotic materials, and they're actually a single crystal that's grown because we can't afford to have any cracks between the crystal. Otherwise, you'll have a fatigue failure, right? And then that turbine blade can shoot out. And sometimes this happens. You'll hear about it in the news. Sometimes they'll just shoot out or they'll get a chip. And so these pieces generally have to be machined, but there's some really tricked operations that go into that. And so I'm kind of jumping ahead. I think I'm going to come back to these slides later if we have more questions, because this is sort of the high end of machining. But I just want to show you guys what's possible, and then we're going to kind of go back to the basic stuff and how do we get here, right? So let's move forward. So we talked a little bit about hardness. I also want to talk about this word called toughness. So both of these are really, really important to kind of understand. Again, I think everybody generally has an intuitive feel for hardness, but toughness is a little different. Toughness is generally how well a material can absorb energy is probably the best way. And so if you can think about like if you were to drop a piece of aluminum on the ground, it may kind of bend, but the surface is going to kind of deform, but generally it's going to take all that energy pretty well. It's going to kind of spring back. When you have a material that's really, really hard, it's very brittle and it's basically not very tough, right? If we could have a perfect material, it would be like diamond hard and it would be like super tough, right? And it would give you a lot of flexibility to kind of push on it hard without snapping it, without creating these ultimate failures. And so unfortunately, we haven't discovered that secret recipe yet, but we've got some really good mixes that get us pretty close and kind of balance these properties out. So again, really like when you're comparing these things, they are different, but they're somewhat related. So just kind of keep that in mind. Probably the easiest way to remember this is carbide is going to be really, really hard, but very brittle, right? And something like high-speed steel, HSS, it's not going to be as hard as carbide, which we saw on that Mohs scale, but it will absorb a lot more impact. So you can actually be a little bit tougher on those cutting tools, and they're not going to just explode in your face. They're going to take it. They're going to kind of bend and give a little bit more. So hopefully that kind of gives you a little bit of an understanding there of when we're talking about those words. So just some additional vocabulary. So MRR, this is a short acronym for material removal rate. And it basically just has to do like if you have a cutting edge, how much volume you're removing and how fast you're removing it. So it's kind of like, guys talk about their cars like, I got 700 horsepower in my Hellcat, right? So like that's a bragging, right? You have MRR, like if you can get a big MRR rate out of a machine, that takes horsepower actually at the spindle, but it also takes this combination of axial depth of cut, which is how deep you're cutting, and your radial depth of cut, which is over from the center line, right? And you can actually go past. You can even take a full radial depth of cut and a full axial depth of cut at full horsepower spindle, and that's how you would calculate that MR. So I know there's going to be some math here, so if you're not comfortable with that, just come to me later, and hopefully we can get like a good intuitive base for you. But I will kind of get into some more math later on, so don't be afraid. It's all good. It's all important. Surface feet per minute. This is SFM. You'll see this a lot as well. This is very, very important in terms of how to drive a speed, an RPM at on these cutters, right? So how fast are you spinning it is directly related there, and you'll see that in RPM, right? Which is down here. So revs per minute. Everybody sees RPM on their car. So again, how fast is that engine turning? That's going to be a really critical parameter that we're interested in. Chips, okay, yeah, not Doritos chips. We're talking about slices of material that are just being removed, and they generally will carry the heat away from the part and away from the cutter. So chips and chip formation is a really big topic. We also down here we have G code, which is short for geometric code, and it's Hopefully you like geometry a little bit because it gets, you know, gets kind of into that. And then CNC, we have computer numerical control. So not that you need to remember any of this stuff, but just to give you an idea. Are there any questions so far, or we're doing good? Awesome. All right. So moving forward here. So just to give you kind of a brief overview to, you know, sort of like show you a roadmap, and then we're going to kind of zoom in on some areas of this as we go through. But this is what you call a milling machine, right? This is a vertical mill. And this is actually really similar to what we have in our shop. This has some certain pieces to it, but basically this piece here can slide up and down. So if you're looking at the PowerPoint there, you're going to have this knee, which right here, it'll move up and down on this column, and it'll give you some height adjustment. This table here can move in what we'll call the X and the Y plane. So those are orthogonal to each other. And then of course you have, you know, your Z as well, which goes up and down. So we have X, Y, and Z. And this just shows sort of what it is. So with a milling machine, you're actually holding what's called the workpiece, and you're turning the cutter. You're turning the cutting, you know, device, if you will. And so that's kind of the general setup there. And then we're going to go in more later on. We're going to talk about tool holders a little bit and work holding, and it all happens kind of in this general area right here. Now we kind of look at something called the lathe, right? And so the lathe actually does the same thing the mill does, but in a completely different way. It's actually turning the workpiece, and it's holding this piece still, right? So this is the cutting edge, and the workpiece that we want to form is actually what's turning. Otherwise, they're pretty much the same thing. You know, generally you're going to use a lathe with circular things because it's turning. But ultimately, it's the same thing. It's just kind of turned on its head, right? And so all these pieces here are, you know, how you would adjust this. And you know, again, you have this piece here, which will actually slide back and forth on a lead screw. And then these handles here adjust your gear ratio. There's actually a huge transmission in this thing with a bunch of really kind of intermeshing gears. And you can actually adjust the speed of what this thing is turning at by playing with, you know, A, B, C, and 1, 2, 3 on these levers. And we're going to talk more about why we do that. But ultimately, it's to set the RPM at what we want to for that given material. So moving forward here, this is some basic support equipment. So what we have is we have the bandsaw here, right? And so this is really important in kind of cutting out that initial shape. You can think of these almost like a lightsaber, right? They just go right through stuff. So we have a really sharp band here, and what we'll do is we'll feed a material into it. This one actually is hydraulically operated, so it'll come down and you can set how fast it drops down, so you don't have to like worry about pushing the material through. You just basically set it on there, and it'll actually like slowly drop on its own, which is really nice. And then up here we have the bench grinder. So this basically has some cutting wheels. These are usually made of some type of a stone. And then over here we have the belt sander. So all three of these are really important in kind of prepping that stock before we can really get started in machine. So here's the bandsaw, and just some general kind of rules of thumb about it. So this is a video about how to fold a bandsaw blade. If you ever find yourself, you need to fold a bandsaw blade. The GIF's in the PowerPoint, so you know you can watch that. It's you know, it's one of those things you kind of learn in the shop, but if you first try to do it, it'll kind of mess you up. So I figured that was helpful to put in there. And you know, really, again, the bandsaw is made for just making that first cut. And how it does it is it uses a blade, and basically the teeth of the blade, if you zoom in, they're kind of staggered. They're not straight in line with each other, and that's called the blade kerf. So that'll actually cut a little bit thicker than the blade itself. And so you have to kind of account for that when you're doing these, when you're using the bandsaw, because again, these teeth will stick out left and right a little bit thicker than the actual band part. And that's great for carrying the chips out, right? Once we start cutting those chips, we want to move them away. We want to carry that heat away. And so the kerf is you know, that's sort of what it looks like there. And these are just different types of bandsaw blades. And so what you'll see is up here we have, you know, one of my favorites is actually the variable pitch one, which I thought I had on here, but looks like it might not be. But they'll actually change the pitch between, which is your distance between. So just like, you know, we see these wavelengths and we see on these oscilloscopes, you see these types of frequencies, boom, 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 right up and down. You can have different pitches, which is just the separation between the peaks and the valleys. And you can actually cut through, you know, a thicker piece or a thinner piece. And generally the rule of thumb is you always want to have 3 teeth within contact with the material at any time. And that's just to spread the cutting forces out evenly. If you try to like go and cut a big hunk with like, or actually let's say you cut like a small piece with this type of bandsaw, you're gonna end up breaking the teeth off because that one tooth has to do all the cutting as it's going through, and then the next one has to go through and do all the cutting, and it's not sharing, right? So what we really want is we want at least 3 teeth to kind of be in contact as it's pulling through the material. So just keep that in mind if you're ever like using a bandsaw and you're wondering if it's the right blade. That's a good rule of thumb. This is a bench grinder. So again, really the big thing about the bench grinder is it's moving fast. It'll definitely take off some sparks, and you're going to see that. And these are really important that we only use these with ferrous materials or anything that contains iron. You do not want to use this with a aluminum piece at all, right? It'll actually get gummed up inside the pores of the stone, and that can actually create like an explosion. It's actually pretty dangerous. So if you ever see someone cutting or using one of these guys with aluminum, maybe tell them to stop. And really how you can tell if you don't know, if you don't see sparks coming off that thing, if they're not bright orange sparks coming off, it's probably not ferrous, right? That's sort of a dead giveaway. If there's no sparks coming off, probably stop and check, and you're gonna see there's a bunch of like gum up in the wheel there, right? And also you can do this with titanium too, which I've done, and the sparks actually come off white. It's very cool. It's kind of like if you go to the golf range at night and someone's got a titanium driver and they hit the ball, you'll see a little white spark shoot off. If you guys want to see some sparks, we have that piece of titanium floating around. We can grind it later, but yeah, or magnesium is a bad idea. Don't do that, right? Because you get that auto ignition temperature, and then it turns into like a 5,000-degree meltdown, and you burn a hole in the earth. So don't do that. This is the belt sander, and it's just like you imagine. It's basically a big belt that moves the sander. But all these operations are important to kind of getting you a piece of stock that's prepped properly to go in and be machined. So, once it's ready, it's going to drop into a fixture. And so this is probably one of if you take anything from today, this is probably one of the more important things to really understand. It's not tricky. It's just something to kind of it'll change the way you think about the world, I think. At least it did for me. So, in anything, we all know we live in a world where there's 6 degrees of freedom, right? We can walk forward, we can walk back or left and right, or we can jump up and down, but you can't really do anything else. You can do a combination of those, but it has to be, some translational movement in the X, Y, and Z. And then you can also rotate about the X, Y, and Z. So you have 3 translations and 3 rotations, which gives you 6, right? 6 degrees of freedom. So anytime we're locking a part down into a fixture, we want to make sure that we control all 6 degrees of freedom. And really the easy way to do that is to think about, say I've got this part right here that I want to lock down. If I take 3 points anywhere on there, I can create a plane. And so that will actually, basically that'll lock down, I think it's like 3 or 4 of the degrees of freedom right off the bat, right? But we'll still be able to kind of rotate, and we'll still be able to translate on a couple. And so by adding in 2 pens here, you can actually stop that movement in there, and you can stop the rotation. And then the last thing you have to do is just move it up to 1 more point. And now if this part is in contact with, again, 3 points to make a plane, 2 points for a pen, and 1 point there for the point, you're actually going to lock down all the 6 degrees of freedom, and then you're going to go ahead and be able to machine it. So looking at fixtures, you'll see this a lot where they'll have, in this particular fixture, I just found this picture online, somebody made this, but this plane right here is what's going to locate generally like the A datum on a part. Go ahead. Yeah, go ahead. You have a question?
Machine without locking all 6 parts of freedom?
You can, but it's probably going to move on you.
This is a risk.
Yeah, I mean, in some cases, if you think about it, like on a lathe, we're actually really not like quite locking down that rotational degree because we have to turn the part. But in the chuck, yeah, it's locked in there. So it's kind of a relative between the work and the work piece and the holder that it's in. That's where those 6 degrees start to apply. But yeah, I mean, again, here you have a plane. We're creating a line across here with 2 points of contact, and then we have this last point of contact here. And so that'll kind of keep your part nice and fixed. These are some overall calculations, and I'm not going to go through like all the detail of it, but just to give you guys a rough idea, if you're using 3 horsepower spindle, which is very common with like a Bridgeport machine, and we're using, we say about 75% efficiency because you're going to have some loss through the transmission and the belts and things like that. And then this is just a conversion factor here, and this is our surface feet per minute. It ends up working out to, it's about 740 pounds that we need to react out of holding onto this part. So it can be very, it can be a lot of force. It's more than you would think. I mean, 740 pounds just to hold onto a little thing that you're taking a cut with. So just to kind of give you guys an idea of where that's at. So these are some fixtures here. This is, hold on tight, we get into work holding. So these guys, this is actually one of my old soft draw fixtures. I actually designed this part back when I got out of college. I did some mountain bike parts, so I had to put the picture in there, We have a chuck, which is made for holding onto round stock. Really the most popular one here is going to be your vise. So you're going to take a block and you're going to kind of fix it in there. And you'll use parallels to set it up and make sure that it's nice and tight in there and level. And the fancy stuff gets into these pneumatic chucks and these custom fixtures, which will have hydraulic pieces that'll kind of move out of the way of the cutter as it's coming through. So again, here's a picture of that. So this piece is actually made to come right off of these pneumatic chucks. This is a quick change pallet system. So if you're doing a bunch of these parts, you can actually put some holes in the bottom, drop it in, machine it, and pull it right back out. So kind of, some faster ways to do the same thing. Let's talk a little bit about tool holding. So tool holding is, stuff like this right here. So this is a Cat 40 tool holder. And I'm going to go ahead and pass this around again. The drill's a little sharp, but if you hold it kind of by this end, it's a nice end, right? So it's not gonna hurt you. But yeah, it's got a little weight to it. So feel free if you guys want to check it out. This is all about tapers, right? So we have spindle taper that is going to pull that tool holder up inside of it. And so each one of these you'll see has a slight taper to it somewhere. We also have the R8 collet. This is what we use in our shop here. This is really popular in a lot of manual milling machines. And again, that taper is right here. And this actually has a drawbar that'll come down, it'll feed, and it'll pull this whole piece up into a taper. And then while it does that, it actually squeezes down and it grips onto the end mill, right, or the drill, or whatever we're going to be going ahead and cutting. So you guys check that out. And then the HSK tapers, those are generally used in really high speed routing machines. You'll see those a lot more common in composites and really probably across the street they might even have some of that stuff, right, where they're doing wood and they're doing that kind of material. So again, this is what they look like inside. You're going to have really three pieces. So you have your tool holder itself, which has the taper. We have the collet, which is a really precise piece. And I have one of these that I'll definitely pass around. So this is the collet, and the actual drill the end mill will go in here. And this is basically just a big spring, and again, it'll squeeze down as we tighten it up. This is a beautiful part. Look at it as you're holding it and figure out how do you make something like that. It's and that's just one small piece of kind of getting this whole machining thing to work. We have to have these little tools to get to the end, right? And then this is just a nut that kind of goes on and holds everything together. So any questions so far? Are we still hanging in? Cool. Yeah. Yes, exactly. Yeah, Dremel tool also has a collet at the end of it. So I did a little bit of research and I actually learned some new stuff, kind of preparing for this. Also, I thought I'd share because I thought the statistics were pretty wild. But if you look at something like, say we're holding these tools and the spindle, right? So you see that drill over there. If that drill is not exactly concentric to the center line of the spindle, it's probably more common really with an end mill. But just imagine for a second that you don't have it exactly on center. And little secret, you don't have it exactly on center. There's always going to be some amount of run out, right? It only takes a very small amount of run out to actually create a huge amount of tool wear. I mean, we're talking 1/10,000th of an inch can drop 10% of your tool life, which is pretty wild. So again, this is a top view of what that concentricity would look like. So this is your cutter not on position, right? So this would be bad. So what we're looking for in these tool holders is we really want to maintain that concentricity. That's really, really important. And then, after you've locked that tool into the tool holder, that tool holder itself has to go into the spindle, and it also needs to be concentric, right? So you have a lot of things that start to add up. And again, if you're not seeing a good result or you're seeing a lot of tool wear, you might have a problem with something like this, right? So this is a nice little chart here. Again, check it out later. There's a lot of information in this. So let's talk about drills. I love drills. Drills are awesome. Who doesn't like drills, right? Let's make some holes. It's the best. Everybody's probably got one of these. Maybe you got one of these in your garage. This is a drill press. This is just a handheld drill. Again, this is using a drill in a lathe. So we're turning the workpiece, and the drill actually stays still this time, which is kind of cool. And then this would be in that drill press that the drill's going to spin. And so, I mean, drills are easily the fastest way to just remove material. We go back to that MRR, right? We want a material removal rate. If you want to get rid of stuff and delete it, drill it. I mean, just drill it out, drill a bunch of holes in it, and it's gone faster than any other way. So they're a really useful tool in the shop. And generally, the cutting surface is only going to be on that very, very front tip. It's called the chisel edge. And I got some pictures of that. And also, coatings can help kind of reduce the wear on the tools. So, you know, the first we call a twist drill was patented by this guy named Stephen Morse. He actually also has a taper named after him, the Morse taper. He's a pretty important guy. This was back in 1863, and so he went ahead and came up with this, you know, idea. Hey, if we start cutting our you know, metal out of this way and we start drilling holes, that's pretty cool. We can drill holes in anything. And so as time moved forward, the first thing we really started playing around with was higher carbon, you know, steels. We started learning about, you know, Bessemer process and a lot of these iron carbon phase diagrams, and engineers are starting to figure this stuff out that blacksmiths have known since the 1500s, right? And so we start adding more carbon, they get harder and harder. And then we start adding cobalt, they get even harder. And then we discover carbides and solid carbides. And then nowadays we've got these beautiful carbide tools that are coated. The coatings can be anywhere from like a black oxide. This titanium nitride is really popular. You'll see that gold color. That actually reduces the friction while it's cutting, and also reduces heat in the tool to kind of keep that drill last a bit longer. Then you have diamond, which is like very, very expensive, right? I mean, everybody knows diamonds are expensive. It's no different in the tooling world. These are like, you know, generally lab created diamonds, but they still cost a lot of money. So I'm going to pass around the diamond tool. Don't lose it. This is a slot cutter, so we'll get into the form of this, but actually on the tip here, these are all coated in PCD diamond. So you know, I guess I can just pass it around like that, but just it's not too sharp, so just, you know, be careful there. So let's get to the point, Kevin. Stop talking. All right, so lots to cover, but again, we talked about that chisel edge, right? So at the end of the day, we're just creating a lot of pressure in one point. We're creating, and pressure is that force that, you know, we're pushing down on something. We have a very, very small surface area at the tip of the tool right there, and so it creates a huge amount of pressure. And the material can't withstand that, so it just starts to give up. Right? It starts to, okay, have it. I don't want it anymore, and you start drilling. So again, the chip formation is really important, and these all kind of add up to get you a good drill. But one thing that I actually kind of rediscovered was, you know, how important using the difference between a standard point and a split point drill. And they look about the same, right? But what's really interesting was this one is actually far inferior, right? So this split point is way, way, way better. You can actually, by using a split point drill, just by having that small geometry change, you can actually reduce the cutting force by about 40%, which is really like awesome. Like it's easier on everything. It's easier on the machine. It's going to be faster, and you can kind of go through. So again, just that small geometry change there makes a huge difference in the way the drill functions. These are some other drills. These are showing the helix angles, and so you'll see like different rates here. And I also have some of these that I'll pass around. And then this is a step drill. This is a really nice piece to have in the toolboxes. This is like 10 drills in one, right? If you want to drill a little bit bigger hole, you just keep pushing up a little bigger, keep pushing through. I don't know. It always reminds me of like a Christmas tree, so I just put that in there too. But yeah, basically you start small and you kind of work your way up, and then you don't have to keep a bunch of drills. You just have the one step drill. So it's good to have for like field repairs, things like that. To peck or not to peck. All right. So this is a question that everybody loves to fight about, but you know, pecking is really like when you start diving into a material, do you want to pull it back out and clear the chips out and then come back in? Or do you want to just kind of go through all the way, right? So depending on your style, generally pecking is not really the right way to do it. And that's, if you have a hole that's about 5D deep, so we'll say 5D is 5 diameter. So whatever diameter hole you're cutting, if the depth of it is 5 times more than that, then you probably don't want to be pecking, because what happens is that drill has to keep entering the material, and it starts to wear out the drill bit. Now you've got 5 or 6 pecks on one hole, which is just that first one when it goes right through. And so that's something to keep in mind. But once you start getting really, really deep in there, and you have a really deep hole, you got to start pulling those chips out. And so then you can start doing those retractions. So that's just something to keep in mind there, Woody the Woodpecker. And then sometimes you'll actually see these drills with through coolants. And the spindle will actually allow coolant to flow through, and it'll come out here and it'll help push the chips back out. So I have one of those. I'll pass that around as well. Spot drilling. Okay, so this is kind of the right way to drill a hole if you want it to be accurate, is you can do a spot drill first. And there's definitely a right and a wrong way to do a spot drill. And the biggest thing is you don't want these edges of the drill to contact and catch first. So this is improper, right? We have too much spot angle on this. What you want to hit is actually the center point, right? This is where all the cutting's happening. And so if this happens first, you have that come into the material. It'll actually help center up the hole, and then it'll give the tool something to really grab into, right? So that's just something to keep in mind there if you ever have to use a spot drill. So here's some, gifts real quick of the, the way that the drill is creating that chip. On the left side here, we have the lathe, and then over here we have a general drill. This is a reamer. So reamers are pretty similar to drills, but they'll actually they'll do the final size of the hole, and they're actually only cutting on this dark blue edge right there. That's all they do. Yes, we have a question.
Yeah, do they center punching is a good tool like
Center, like, to punch it first is a very effective. It's kind of like a cheap spot, right? So you're not necessarily, they actually sell a drill that's a spot drill and it has that angle in it. But if you don't have one and you just want to punch it, yeah, definitely. Because you want that center to have something to kind of set up into. As long as the edges of the tool don't catch first, like the edges of the drill, that's the biggest thing. So just keep that in mind. Don't punch it too deep. But yeah, reamers themselves, that basically they're really good at finishing, getting the hole the right size and keeping it straight. So I have some reamers as well. So these are all the different shapes. These are end mills. So let's get out of drills for a little bit. We'll move into end mills. So end mills are kind of similar, except for instead of cutting on the face, they cut on the end, right? They cut on the side. That's why they call them end mills. And you can have a ton of different shapes with this. So you'll see the coatings and those carbide materials. All that stuff still applies, but now we're in the end mill world. So what you'll really see is like aluminum stuff. You're going to see usually has less chip or less flutes. So that's the number of kind of these spirals that go up the side, and that's to get more chip clearance. And then if you're cutting wood, these are kind of interesting. The plastics actually just have one flute, which is kind of a weird shape right here. But it's just to kind of get that chip clearance maximized. And the wood actually has the flutes are reversed. They're going the other direction, and they're actually meant to kind of push the chips down rather than pull them out. So all of this kind of has its own place and purpose. But again, key things really to keep in mind are just the helix angle and kind of how much core is in the chip here and how much relief. So again, helix angle, probably going to jump over a little bit of this stuff, but again, come back and check it out. Something to keep in mind, so more flutes generally is more for the exotic materials. Steels are usually going to be around, you want to use like 4 or 5 flutes for that, because you need a nice core in the middle to be pretty strong, but you also need good chip clearance. And then aluminum, again, less flutes, the better. Usually 2 or 3 is great for aluminum. That just is going to get the chips out. And again, when we talk about the core, it's just that piece that's in the middle that's not carved out. It's not missing any material. It's solid, right? So these are your flutes here, and these will pull the material right out. Chatter. So chatter, you're going to see when you're doing it wrong. So this is a bad sign here. Nobody likes to see chatter. And really what it is it's a combination of a bunch of different factors creating some type of resonance on that surface. So that resonant frequency is going to happen differently. It's all different systems have kind of a different natural frequency, but when you hit that natural frequency, everything starts going really wrong. And usually what you see chatter here, right? Up here we have a way to measure that. We actually use this thing. It's called a profilometer, and you basically put it on there, and it'll drag a little needle across, and it'll tell you how rigid this surface is, right, or how bumpy it is. And you can actually equate that to a real number. So just something to consider. Ways to kind of overcome that are pretty clever. Again, that natural frequency, right, happens when you start, you jump on the bridge and you start creating that, the bridge starts getting really big, right, or the trampoline, and you start bouncing somebody. What you can do is you can actually bounce just a little bit different times. So what they do is they end up actually tweaking when they're making these end mills. They'll push a flute just like a degree or 2 off, like you'll see here, like 0.8 degrees or 0.5 degrees. They'll push it just a little bit off of the next one, and so that way when that flute comes around and it hits it just a little bit later or just a little bit more early than the last one did, and that kind of breaks up that harmonic resonance. So it's a pretty cool solution. Again, you can also change the helix angle as you go up. So they can start out really aggressive, and then as it goes up, it can change. So that'll actually help with like the extraction of the chips as they come out. And again, that plays with the chatter. So all of these are like little variables that kind of happen to help reduce that. If you ever find yourself cutting carbon fiber, this is a really nice tool. This is called a compression cutter. And it actually has fluids going one way and then fluids going the other way, and it'll push and pull, and that'll kind of balance out the forces so you don't get any delaminations on the part and pull up the fibers, and you want a nice smooth edge at the end. So just keep those in mind. Those are nice to have. This is some honeycomb here. This is really tricky stuff to machine. Any ideas on how to hold this? Like looking at it, what would you guys do to hold on to something like that? What's up?
Temporarily bonded to something.
Yeah, you could tape it, right? You could do like a lot of stuff. We actually had a really trick way of doing this. We would fill it up with ice or water, and then we'd put it on a chuck and we would freeze it, and that would actually create ice in there, and we would just machine right through the ice, but that would hold it in there. That's kind of an interesting, solution to a really tricky problem. But we need this stuff to get on the plane and fly. They use this in all over aerospace and quite a lot of other industries too. So yeah, just fill it up with ice and freeze it, and then once you're done, you just let it melt. You got yourself a part. So work holding is all about being creative, right? And really coming up. Go ahead.
What's the application of the honeycomb?
Yeah, so they'll use this in like a lot of aerospace inside the wings and things like that. And you'll actually see that carbon fiber piece that's going around. You'll see like an edge of it. You can't really see, but that is actually honeycomb that's in there. But yeah, no, great question. It's basically very rigid, so you can stand on this, and it's very lightweight, right? So it's a really strong. And again, it kind of comes from nature, right? The bees actually make the honeycomb naturally. And I learned something recently about how they produce this. When they actually make it, they're not programmed to do this nice, like kind of hexagonal pattern thing. They actually make it in a circle, and then as it dries, it just naturally hardens up into a honeycomb shape, which I just learned that. I thought that was fascinating because nature really just has a way to find like the strongest shape for, weight ratio. So we're just kind of stealing that, and we're using it where we want to, but it's pretty cool. Otherwise, you still need to machine it. This is that Inconel stuff we were talking about. This is a really exotic material, and this is actually using ceramic inserts in the cutter. And so this is a lot of fun to watch in person. If you ever get the opportunity to go to a machine shop and they're cutting Inconel, and get in the room. It's fun. It's a fireworks show. It just shoots these red sparks everywhere. And again, we use these ceramic inserts because they need to take the heat. And this piece does not take the heat. It just that's the point. The Inconel is really, really good at high temp resistance. So the workpiece doesn't get hot, but the ceramic inserts end up getting super hot, and you're shooting all these things around. So I thought that was kind of a fun video to share. You get into specialty cutting tools. So again, pretty much any shape you can imagine, you can cut it. So I'm not going to spend too much time because I know we're starting to get towards the end here. But I just want to kind of jump through the slides probably a little bit faster than I normally would here because I like to talk and I burned the time already. So boring bars, right? These are really good at finishing out holes. So I'm just going to kind of show you guys what's in the presentation. And then later, let me know if you have any specific questions. Thread milling is super important. So thread milling is actually really important when you want to cut threads, right? So how this works is it'll actually come down and it'll come into the hole, and it's a little bit undersized, and it'll actually cut the threads. And that'll avoid, breaking off taps inside of parts, which is no fun if you ever have to get a broken tap out. And so how it works is it'll actually come into the part here and it'll cut that thread. And it can be done. And again, you're spreading out the load all over. So all those teeth are kind of doing the work, and you can save a lot of time. This is micro machining. So again, these can get down, this is the world of the small, right? These can actually get down to 1,000th or 1 mil. The funny thing about that is they'll actually sell these to you as 1 mil plus or minus 1 mil tolerance. So if you get nothing in the box, you got what you paid for, right? Cutting forces, this is actually kind of interesting. So just something to keep in mind. Doubling the diameter will actually reduce the deflection by 16 times. So it's not like 1-to-1. It's a significant amount. And so when you start getting into those small tools, this is something to keep in mind. That the tool deflection is actually a huge factor as you start to cut through. Surface feet per minute. So the SFM is again, we calculate that with our diameter and our RPM. And a way to think about this is how fast the actual surface is moving. And so, like say I take this piece here and I'm spinning it, right? It's spinning. Well, one way to kind of measure this Because if I put this down, it's going to roll, right? It's going to roll along a flat surface. And so that is actually a way to kind of visualize surface foot per minute. It has to do with the diameter. So you're spinning this guy up. And then if you were to take that and kind of put it down like a car tire, it's how far is it going in surface feet every minute. So it has, again, to do with your diameter and your RPM. But that's a really important parameter when we're programming. And just a way to use it, it's a bit of an eye chart, but a way to check this out is if you're machining steel, for example, or let's do aluminum, right? So we're doing aluminum and we're cutting a non-ferrous material and we're using, like uncoated carbide. We can go up to 1,200 plus surface feet per minute. So what you'll do is you'll kind of match up what material you're cutting and what your cutter material is, and you'll be able to figure out what those recommended speeds are. How fast can you spin that thing and have it hold up? And then when you're pushing through the material, this is how fast you're going to push through. So this is, again, a lot of chart work. But say you're cutting a 304, stainless steel at 200 surface feet per minute, you can actually calculate how much how thick each chip is. Yeah. Unfortunately, time is going to be tough. Too much to cover. It's a big world. And those speeds will actually change too. So if you're cutting in a straight line, they're going to be just like what you would calculate. But something to keep in mind is if you start going on the inside of a pocket, you actually want to slow the feed down. And there's a little bit of a calculation for that compared to on the outside, because again, we're controlling the center point of the tool, not the edge. And so you got to kind of account for where you're at in the pocket. This is climb cutting versus conventional. So generally, you're going to always want to really climb cut unless you're doing, there's some really specific case hardened materials, things like that, that you'll maybe want a conventional cut. But if you're ever questioning, start with the climb cut. And the way I always think about this is the direction of rotation relative to the feed rate, right, or the feed direction. And so this almost looks to me like kind of a wheel doing a burnout, like in a car. And that's just a really easy way to remember it. This is kind of a burnout, but it's moving backwards, right? And it's trying to go forward. So, but just imagine like you're spinning and you're feeding in that same direction of the spin. That's going to give you a good climb cut. And that helps a lot with your surface finishes. Again, we talked about the milling machine. This is the same thing, but it's a horizontal milling machine. So there's lots of different shapes and sizes for this stuff. This is a lathe. This is a mill turn machine. This is super cool. This is actually a lathe and a mill at the same time. Like, how awesome is that? Way too much to program though. And they get very complicated. As you can see, it's not somewhere you want to find yourself inside. Talk about coolants a little bit, right? And those will kind of automated versus manual machining. So there's quite a lot of advantages to both. Manual is going to save you a lot of time and like one-off prototype stuff, but the actual automated CNC part can save you a lot more in production. So talked a little bit about how to kind of hold those 6 degrees of freedom. We have the Cartesian coordinates here. This I'm not going to go into, but these are your G codes and your M codes. I think unfortunately we're not going to quite have time to do the G code programming example I had for you guys, but it is here if you're interested. You can basically kind of go line by line through it. So you're going to start at a point in space and you're going to basically tell the machine to kind of move up to a certain point here. So you have these GOO will line up with a rapid move, and that'll move you up to point B. A GO1 is a linear feed move, so that just moves in a straight line. A GO2 is used for a circle move, and then you're back in, and you can kind of go line by line and basically trace your steps out, right? So it's not as complicated as it looks. It's just one piece at a time is really the biggest thing. So nowadays, what we do is we actually program all this with a computer. So that takes a 3D model, and then we will go ahead and we'll program in tool paths. And instead of doing each line one at a time by hand, and back from the ticker tape stuff, which is really slow, now the computer will actually use algorithms to figure out what the shape of the material is and how to feed down into it. And ultimately, we just adjust the parameters of our surface feet per minute. We adjust our axial and radial depths cut, and then we'll go ahead and kind of carve everything out and put it in the machine. So again, this is in here. I'm happy to go through it if anyone's interested. There's some 5-axis machining, which starts to not only do X, Y, Z, but it'll actually move things off at an angle, which can be really helpful for finished contouring on parts. And you'll see that right here. Right? So some pretty unique motion. A lot going on there, right? Everything breaks down. Just remember this too, right? The 6 degrees of freedom, and everything is a straight line or a circle or some portion of a circle. And that's all we're doing. We're just doing GO1s for straight line moves and GO2s or GO3s for circular interpolation moves. And you can make any shape you want because it's always some type of arc or always some type of straight line. So that's just a really nice way to look at it. This is EDM machining. This is used for very tight tolerance parts. And this is cool. Actually, the heads can move independently. So these are both CNC programs to do those tool paths that we were talking about. And the way this works is it'll actually create, the wire comes through and then it'll actually have a small gap between the wire and the metal, and it'll create an electrical potential between there. It'll actually pull the electrons off of the metal, and it starts to take the surface down. And then as it moves through there, you end up cutting these parts, and they're just amazing parts, right? You can see here, they can drop right in. The tolerances are perfect, right? It's the only thing in there is just a little bit of air, and then it just disappears. So EDM is a really nice, it's a completely different look at machining. It's not necessarily using, twisty stuff to cut other twisty stuff. This is a completely different approach using electrical potential. So, again, quality plays a big part. We use AS9100 to kind of inspect these parts and make sure that we have good repeatability in our processes. Machine calibration, that's a whole other topic, very involved, but you basically want to make sure that when you tell that machine to move 1 inch, it's actually moving 1 inch and not just like 1 inch and a little bit. And so you have things like backlash compensation and tool length and probing and all these different types of things that you can account for in the machine control. Some overviews of our shop. So this is the stuff that we can kind of do in our shop. We have one of these Bridgeports. It's a great machine. It has a variable speed spindle, and the table can go in X, Y, and Z, right? So we can move things up and down. You guys saw this kind of early on in the presentation. And again, it uses that R8 collet that kind of made its way around. We also have drill presses. We have grinding wheels. We have a bandsaw in there. And we can just kind of do some standard hole tapping and threaded repairs and things like that. So just to finish up here, there's always many decisions to make when you're kind of really considering machining. You guys probably just got a small taste of it today, but you see how many variables go into it. And so all this stuff is things to consider. And it really just comes down to nothing's free, right? Everything has a trade-off. And so you're seeing, if you want to go faster, maybe you need to spend a little more money. If you want more rigidity, you're going to lose toughness, more hardness, less toughness, things like that. There's always a trade-off. And there's always room for improvement too. So we're still going to be learning about this stuff for a long time to come. And that's pretty much all I have for you guys. So we'll do, I think we have like 2 minutes technically for questions, but go ahead and ask if there are any. And if not, come by later as well. So sweet, no questions. Go ahead, Ben. What's up? Yeah.
Accessory tools or vacuums.
Yeah, that's great. They actually do. Yeah, they do have. It's kind of cool. They actually will sell like a fan that will have these like retractable blades that'll go up in a tool holder. And so once you're done with your cutting tool, the tool holder will come through, pick that up, and it'll actually just blow off the whole area, blow off all your coolant and stuff. So they sell things like that, and it just uses the horsepower on the spindle, and you can program your own tool path. So that's kind of a unique way to do cleanup. The old school shop vac never fails, right? There's a lot of compressed air getting used. The coolant usually has its own tray underneath the machines that'll recycle the coolant and filter out those chips, and then it'll feed it back in so that you're getting the most life out of it. But yeah, great question.
Chip collectors on the CNCs.
Yeah, chip collectors, exactly. Anybody else? Yes, Ned.
Do you have a sample of that wire
The EDM stuff, I wish I did. I used to have one, and I don't anymore. I do have some other cool stuff. Feel free to come up after this is over. This is actually the first part I ever CNC programmed here. This is called the Turner's Cube, and it's a cube inside of a cube inside of a cube. And I actually cheated. I did this on a mill, and I did a CNC program for it. I was mostly practicing, but you're actually supposed to make this on a lathe, and so that's weird because it's a square part. And we talked about lathes; they hold the part and they turn it. So you have to kind of quiz yourself: how am I going to make a square part on a lathe with all these circles inside? But this is actually a test for a lot of like apprentice machinists that when they're first learning. All right, make this, and you have to go figure it out, which was kind of fun. I like I said, I sort of cheated with the CNC machine, but you get the idea. Pretty cool. So come check this out. We've got more titanium up here. This is a big piece of machined titanium, so you can actually see the tool marks in it from when it was getting cut. It's got a little bit of burrs on it, but I tried to clean it up. But yeah, come up, check this out. It looks heavy. It's actually lighter than you would think. This is for a helicopter blade, so this is what holds the blade on as it spins around, right? So pretty cool. We've also got some more parts here, so lots of cutters, different things like that. So Any other questions so far? Or?
Thank you very much.
Thank you. You got it. All right, thanks, guys.
Good job.
A lot of stuff in a little time.
It's a lot. Yeah, it's like too much, but I tried to rip it. All right, thank you, guys.